Okay, so what we developed yesterday using all this lovely mathematics that you're all really good at is a new formula for standard deviation. Okay, so you've now got two formulas for standard deviation. So if I get that off the screen, the first one that we have from before was just, so find the difference of each point from the mean, square it, divide by the number of points, and then square root, but I've forgotten to add up all the points. Yes?
Why can't you just use that one?
Why can't you? Good question.
I don't like this other one.
All right. The other one is derived from that, as we did yesterday, but it's the sum of the squared values. So if you take all the individual values that you've got and you square them, right, and then you subtract, so that's the sum of just all the values divided by number of values, which is the mean, and then you square that. So we've got two options. This is always useful to have two options depending on what information you're given. Okay? So this one, as I said yesterday, is based on the summary statistics. Okay? So what does this one require us to have? The first one.
The mean.
So we have to know the mean, which is fine because we need it for the other one as well. Okay. But what do we have to do? We have to do every single point, subtract from the mean,
Yeah.
add all those up. So we have to have every single point, yeah? Because we have to do that, then square them, then add it up. So what's different about this? Anything or nothing useful? Yeah?
You don't have to do that.
We don't have to do that. All right? You notice how we've got rid of that every point has to be subtracted from the mean individually bit. Yeah? So it reduces some of the workload maybe. So let's have a look at how we could use it. So we'll look at example 4, which is on page 89. All right? And we'll show the difference between what you can do with this one compared to what you had to do with the other one. So we've got the length of time t in minutes for a skier to travel down a mountain follows a normal distribution and is recorded on 15 runs. The summary statistics are the sum of his runs is 129 and the sum of them squared is 1,181. Okay? Find the mean and standard deviation of the times taken for this ski run. Right? So actually, all you're told in this case, you're not told the individual 15 runs, you're only told what it is in total. All right? The summary statistics. And then you're told what happens if you add them all up when they've been squared. Now, is that the same thing as, if I add up a list of numbers and then square the result, do I get the same answer as squaring all the numbers and then adding them up?
No.
Sure?
No.
No. Yeah? Never sure? Especially when a teacher says, are you sure? A teacher might just be thinking, right, it's a yes or no answer. So there's 50-50 chance and you might just go, yeah. Should we do a trial? What if we've got 3 plus 4 plus 5? What's the answer? 12. Right? And if we do 12 squared, we get? What if I do 3 squared plus 4 squared plus 5 squared? What do I get? So 9 plus 16 plus 25. What did you get?
50.
So the answer is not the same. Okay? So bear that in mind when we look at this, the sum of the values squared. All right? But anyway, let's work out, it says find the mean and standard deviation. So we've got to find from this data the mean. So how can we do that?
That. Oh, that.
So we've got the sum of values. Yeah. So we just do
Divide by 15.
the sum of values divided by n. So that's 129 divided by 15. So the mean is 8.6. I mean, it's in the book, isn't it? But you can check. All right. So then we have to find the standard deviation.
So we should use that one.
So now we've got standard deviation. Well, we've got to do the square root of the sum of x squared over n. So what's that? That's 1181 divided by 15. And what did we say this one was the same as? The second part?
129 over. Oh.
So this is just the
mean.
same as the mean, isn't it? It's the mean squared. So actually we've got 8.6 squared. Which you can try confirming, but they say in our book that that is 2.18 minutes, because we're dealing in minutes. All right. So this is an interesting what people then come up with. So we've got an example. It says, make a generalization about the times for the ski run. This is what we talked about yesterday. Hey?
Did them copy? Did them good?
How do you know?
2 point. Yeah,
Was he fast?
That seems pretty fast.
Really? How long's the ski run? How do you know if that's faster?
Because a run.
That's like saying, oh, I ran yesterday. It only took me 5 minutes. Brilliant. How far did you run? Oh, just from one end of the room to the other. Well, that's not fast then. But if you then said, I ran 10 kilometres in 5 minutes, well, wow, that's pretty quick. So we don't know what the ski, so we can't generalise about that. That's not a generalisation we can make. Do you remember I said to you about the statistics project you did? Do not make assumptions based, unless you have the evidence to say. You can only write things that you have the evidence to back up, right? So what are they saying there? Their answer is, well, 8.6 minus 2.18 is 6.42. And they're saying that 8.6 plus 2.18 is 10.78. And they're saying, therefore, 68% of runs are between those values. Where does that come from?
The IQR.
No. That thing with a massive title, so I ought to know what it's called. The normal distribution. Okay? Do you remember? So what have I got? What is 8.6? Is the mean, and 2.18 is the standard deviation. So I've got the mean minus 1, and I've got the mean plus 1 standard deviation. So if I go all the way back up to this look, basically, I've now got other values that I can put here. Oh, I'll do that. Right. So now I can say, let's just stick with that I can say the mean is not 5 in this case. It is 8.6, and a standard deviation is, so 2.18, did we say? And 2.18 below. Okay, so these are the values that they're talking about, above and below. So not 2.8 and not, it's the ones we wrote down. So we now know that 68% of his runs fall within those times. And that's it. That's the only thing that's an inference I can make. All right. Why would that be important? Why would I want to make that kind of statement? Yeah.
Because you don't know exactly what it is, so you don't know exactly what his times are. So.
Well, that's more like a problem. But why would I want to consider that? How many of his runs were there? All right. Well, I tell you why. Because it's a skiing thing, and I come from. I was 10 years in the mountains of Switzerland with lots of skiers. And I know that ski instructors every year have to pass an exam, and they have to be within a certain percentage of a professional racer, downhill racer, to keep their license. And therefore, if he did these 15 runs, at least a certain percentage of them would have to be within a certain time. So we might want to analyse it and go, right, this is... if I said at least 70% of your runs must be within this time frame, would he be okay?
No, because it's 78.
So would you say like?
Say it again, sorry. Why they haven't done it? Well, you could. Remember that word accurate. Be careful with the word accurate. It might be more information, more detail. It's not necessarily more accurate. Accuracy comes from the fact that have we rounded any of these numbers? Not, have we?
I don't know.
And we're measuring to, what would 6.42 minutes be? Exactly. So are we measuring to seconds there with 6.42 minutes or even more? Or because it's not, you all know that's not 6 minutes and 42 seconds, don't you? Mm-hmm. So if you're looking around going, what?
It's 6 minutes and 42 hundredths.
It's 6 minutes and 42 hundredths. So you can do. So it's actually less than half a minute, so it'd be less than 30 seconds. Okay? Just remember that with time. Yeah. Because how many seconds make a minute?
60.
Not 100, yeah? So 0.4 is 4/10 of a minute, which is actually, what's 1/10 of a minute? 6.
Really?
So 24.
So it'd be 24 seconds plus 2 hundredths, so, yeah. But you get the idea, it's like someone was saying, it's 6.5 is 6.5, and 6.5 minutes is 6 and 30 seconds. All right, so just going back to that is the only inference that we can make. 68% of his runs are between. Or we could say, what percentage is within 2 standard deviations? Do you remember that one?
98. 95, 95. It's 95. It's 95 for sure. It is.
95, yeah.
95.
I
Yeah?
know where it is.
Because 3 standard deviations was 99.7. By the way, if you go and look into that in a bit more detail, you'll see other numbers which are much more accurate. They give you actually the 68% is a rounded percentage. All right, it has been given some more. Does that make sense? Should we go through example 5 as well, and then you can get on, just for anyone that... what am I writing that for?
Did you?
I didn't really understand.
I don't know what. I'm writing that because I'm doing sigmas. I don't know.
It's up on my table before that too.
Oh, yeah.
It was up there too, yeah.
So we've got the summary statistics for a class of 15 students.
I told you.
Okay.
What?
I do that.
15 students. Test marks are. So the sum of the test marks is 930 marks. And the sum of them squared, well, that's 59,146. That's a lot of marks. 15 students. Calculate the mean and standard deviation. So again, what's the mean? The sum of them divided by 15, and we get the answer 62 marks. Okay. The standard deviation then is the square root of the sum of them squared divided by how many there are minus the mean squared. Okay. So you end up with an answer of 9.95 marks. Right? So using our summary statistics. So this is where we take it a step further. Are you with me at this stage? Right? It's the examples in the book. Any questions on that so far? No?
I don't know.
It then says, gone. I don't know.
I'm just looking at the numbers, like I don't know what's going on.
Yeah, I don't really know what's happening. I'm just looking at the numbers. It's like, okay, and I'm writing the numbers
You
down.
know, like I'm not following. If you only do this on my own,
I would not be able to do it.
Where are the problems? What?
This entire, this. I
Yeah, but
did
forget
not-
that. You're focusing on that and your head's down and you're going, I'm not listening to anything else you're saying. So tell me what about this bit. So I did say forget about the deriving it. Some of you will get that, some of you won't. But we've been given this formula, we just have to use it. All right? So the formula that we're using.
I'm just confused because like when we were doing this before with the other formula,
Yeah.
like we were being given much different information.
Yes.
So it's
But you were being given all of the raw data.
Yeah.
And what are you getting this time? You're
like just the thing.
Yeah, you're
sum
just
of X
getting
and the
what
sum of X.
all those numbers added up equal to.
But then, well, okay.
And then you're being told, if I square all those numbers and then add them up, this is what I would get. So you're being given less information because someone's already done some work for you.
Like the first 3 steps that we did with the other equation are already been done here.
Yes. So if you get all the raw data, you'd use the other one because you'd have to go through the process. Like Bella said, it's a case of some work has already been done for you here. All right? And mathematicians were always in that situation. You've actually gone and looked up data. How many of you found data where all the work had already been done for you? The means were already calculated, the graphs were already produced, but I'm still asking you to do some analysis on that. Now, if you're given raw data, you start from an earlier point. So all we're saying is, to work out standard deviation, another option is the sum of all the values squared divided by the number of values. And then you subtract, well, the sum of x over n is the mean, and you square that. And that, for those of you that get the fact where this comes from, we did the derivation to show that this is perfectly legitimate because it comes from the other one we had. It's not just a made up, this is what mathematicians do. They link things together and come up with a different form so it's more useful in other senses.
Is that n the mean?
No, n is the number of values.
Wait, but then,
Oh, the n.
so it's like 15.
So n is 15, yeah.
Okay, but then and then the x is the
X, we don't know. It's the sum of all the x. So x would be each individual score. And we don't know that. All right? All we know is that if we add up all those 15 results, I get 930 marks. Now you might be struggling, so why would you do that? Why would I only give you them added up? Yeah? But this is what we're dealing with at the moment. This is what the information we've been given. So it's like there are 15 students. I don't know what they each got. Maybe I don't care. But I do know that if I add all their results up, they got 930 marks. I can work out the mean mark, which is 62, because I divide that by 15. Fine with that? So the mean is 62 marks. All right. I'm being told that if you square all the marks and then add them up, you get this number, and that's useful for finding the standard deviation with the formula. So I've just chucked that information into the formula, and that tells me that the standard deviation is 9.95. Right. So then we're then told there's a second class. So we're going to go through it again. All right. There's another class in this example. This time, the second class is 25 students. So that is n. So n equals 25. All right. Has a mean, we're being told, of 63.5 marks. So are they generally better or not? Yeah, the mean is slightly better. So we could say that class is better. But what do we know about that now? Why don't we make that kind of jump statement? There's more students, and we already know that just the mean does not take into account the spread of the data, yeah? So it might have more students that are better, some students that are better, but it might also have a lot of students that are worse. And how can we do that judgment? We would need to calculate the standard deviation. Yeah, that's what we've been doing. Okay. So we are told, however, that the standard deviation is 12.5 marks. So what can you tell me about the difference between 9.95 and 12.5? Sam? There's one obvious statement. Bella?
That's 68% more like dispersed in the.
Oh, don't try and overdo it. I'm not asking for that. Just it's bigger. That's all I'm looking for. You know, 12.5 is larger than 9.95, and what does that mean in general speaking?
Spread out.
It's spread out. Yeah, the mean is less useful, reliable, not accurate. Be careful with the word. Yeah, the 25 students are more spread around the mean. Okay, that's what we're being told. All right. It says calculate. So this is where we need to go back. So calculate the sum of x squared for the second class. Yeah.
Well, first, wouldn't you find the sum of x? So you do the mean divided by the number of students.
And why are you doing that?
I mean, yeah. To find.
But we
the
can't,
numbers.
remember what we said, we can't take the sum of them and square that number and get the same answer. We've already kind of come across that, haven't we?
Yeah, but just to find the other one, the sum of x.
Okay. So why are you doing that? Because we're going to chuck it into the
Yeah.
formula. We're always using the formula and putting in what we know. So the sum of x squared is what I want to know, divided by n minus the sum of x over n squared. Now, you might now look at this and go, actually, I don't need to find the sum of x, because what is this again? That's the mean. Do I have the mean? I have that. So actually, filling the information in here, what do I know? I know that the standard deviation is, so I've got 12.5 equals the square root of the sum of x squared, which is what I want to know, okay, divided by what? 25. And that's minus, well, this 63.5 squared. Okay, so now I need to rearrange that to figure out the sum of x squared. Hence testing all your algebraic ability. So, first step. It's in the book, so clever ones are you. What did you do first? Get rid of the square root. So we're going to square both sides. So I get 12.5 squared is... Say again? 156.25. So that equals all of this minus 63.5 squared. What can I do now? So I'm going to add the 63.5 squared. So then I've got 156.25 plus 63.5 squared, and that equals the sum of x squared divided by 25. What am I going to do next? Okay, we could do that. So what do you get? So what is, just do it in one step, what's 156.25 plus 63.5 squared? Say again. 0.5. Okay. What's the next stage then? Times by 25. So I've got 4188.5 multiplied by 25, and that equals the sum of the x squared values. So that will be okay. Okay. So we've worked out that. Now the next stage, question C, says calculate the mean mark of all the students in the two classes. Yeah.
You just see now you find the sum of all the x.
Can we do that? So there is another, you'll see in the solution, there's another thing which was in that other explanation that we didn't consider, so this is where we're coming up with it now. So there is another thing here which is the sum of a first set of values. You're looking at the answer in C. The sum of the first set of values plus the sum of the second set of values divided by the number of plus, so that's like the joint means, right? Well, what does it say in the book that is equal to? So that is just equal to the means that have been added together, 1 plus 2. All right? So I'm looking at page 90, the solution. All right. So, as Bella's been saying, we can now look for the sum of the sets of data. So what was the sum of the first set of data? Well, we were told it was 930, right? Do we know what the sum of the second set of data was? Well, we can work it out because we did know that the mean was, and we knew that there were how many people? 25, so that's where the mean, so that's the sum of the first set, that's the sum of the second set. And then if we divide that by the number in the first set is 15, the number in the second set was 25, okay, and 1 and 2. We do that and we get the means together, 62.9, which has been rounded. All right. So if we've got two separate sets of data, we can combine them like that. It's not hard. It's nothing too over the top there. You just take the two totals, add it all together. Well, you know that anyway, don't you? Just mush it all into one lump and divide by it. It's all that is, isn't it? It's just a way of writing it. All right. And then the important thing for you, compare the performance of the two classes on this test. Assume the test marks follow a normal distribution. So, just read what they're saying and see whether you're happy with that. The mean and standard deviation were both slightly lower for class of 15 than the class of 25. Assuming that test marks are normally distributed, 68% of students in the first class would be between those values. For the second class, marks were between those values. What do you notice about the 68% for the second class compared to the first class? There's a larger spread of those two numbers, yeah? Right? Do you notice what's not there in that answer? A favourite breakfast?
Eggs.
Waffle.
Waffle? Oh.
There's no waffle there. There's no making up stuff that has got nothing, no evidence. Hey? It's got everything that you've been told about with nothing else.
Waffle.
All right? There's no waffle in there. There's no... Well, one class probably had a missing lesson and their teacher didn't listen to them when they said they had too much homework. Right? And then I forgot my calculator, so that probably didn't help the first class. I'm not. It's a general thing, isn't it? Lots of people. You know, I sat there. Yeah, well, if you think it's all about you, that's fine.
I know that you're attacking me.
I'm not. I could be making a point that you didn't do your calculator. Right? Who hadn't done their homework? So, and the other two? So, who's brushing their hair in class?
Eggs.
Eggs?
Eggs.
All right. So there's nothing, there's no extra stuff. It's just the basics.
I'm good.
All right. Now, you guys